Hi, my name is Uganze Matthias, and I'm working with Nasarika 3. We are going to be discussing adversarial machine learning, and we are group 27. To give you a brief introduction on adversarial machine learning, this is a technique in machine learning aimed at deceiving a learning model by manipulating input data either subtly or overtly with the goal of causing the model to make a misclassification. As you can see in my image here, we are having a robot or a learning model, and then before it could classify or distinguish between a dog and a cat, and then after adding some perturbation to a dog, it could identify it as a cat, which was misclassifying a dog image as a cat due to adversarial attack. So in this context, we are going to be discussing events or ways and the theory behind adversarial machine learning, where attackers alter inputs or the code of a machine learning model, and then could misclassify or give bad output of the data being trained on. So as machine learning is used in a variety of applications, it also has advantages and disadvantages. So one of the advantages we can say it's used in by machine learning engineers to find vulnerabilities within a machine learning model, and then they are fixed before attackers exploit them. So during the training process, uh, the machine learning engineers can try to trick around the images, audios, and other stuff, and then they see if the learning model will still classify them correctly or it will misclassify them, and then it is fixed. Then also on the negative side, attackers usually use this technique to execute attacks on machine learning models to cause malfunction, and then they can also be used in cybercrime. So in this case, you're going to be talking both the positive side and negative side. An example here, we can have an automated company which is teaching its automated car how to identify a stop sign, and would feed thousands of pictures into the machine learning algorithm, and then this car will be able to identify a stop sign when it comes across it. So but an adversarial machine learning attack can manipulate the input data, and this context the stop sign, by getting either a different image and then label it as a stop sign, and then when this model comes across it, will misclassify it as a stop sign, and yet it means something different. In my image here, I have that the input image was a stop sign, and then it could easily identify it as a stop sign. But when the model, when adversarial noise, what I can call perturbation, was added to the image, it couldn't classify it as a stop sign anymore. It could classify it as a yield, which is a malfunction within the system. So in this case, the system will be failing, and in case this car is deployed, it would cause accidents on the road because it will be misclassifying the stop sign. Then I can give a description of how adversarial machine learning attacks work. The major aim is to either protect the model from attackers, or attackers using the model to cause malfunctions. So in the side of the attackers, forming impacting the model to model's performance so that it can misclassify data or make faulty predictions. So attackers will either manipulate the system's input data or they elect to tamper with the model's code so that it can be able to misclassify or give bad output. So on the side of uh, what manipulating input, so the attackers can modify, make slight changes on this input. For example, if it's an image, they can label it differently or add what we call noise, which can make the model misclassify the image. For example, like I explained before, using the image of a dog and a cat, the model could identify that this is a dog and this is a cat earlier, but when they added noise to the dog image, the model could classify it as cat, which was a malfunction and which is wrong. Then we can also have a coincidence of someone having, for example, a voice recognition system, which was speech recognition, for example, yeah, whereby I can speak to the model. For example, I can say good morning, and instead of it responding to good morning, it would give a different response. When the model gives a different response, and to analyze the data it has received, you find that due to noise, the good morning greeting wasn't actually perceived within the model, and it is giving out a different output. Uh, Then we can also have where attackers or corrupt a model during training or can target a pre-trained model that is already deployed. So when attackers do that, they can get an unsecured model and they access or alter the architecture and parameters so that it can no longer work as it should. These attacks can be in a way that, for example, if I have a function where the model which I wrote within the model, and this function is supposed to guide the model in classifying images, and then the attacker modifies that function, meaning that the model will misclassify the images not because it has seen different stuff, but because within its code it guides it to do something else. So that can be two ways in which attackers can be able to alter either input or the code, the system's code, and then the model can be able to misclassify the input and output. That's how one way adversarial machine learning works. But then we can also have a situation where the machine learning engineers are training the model, and then they are trying to identify vulnerabilities or faults within the model, and then they can also use the same methods by altering images and also by modifying code and then finding ways of fixing this so that in case it comes across to uh, an attacker or a cyber criminal cannot be able to make those modifications within the code. Then we have types of machine learning. Under these types, we majorly have three types of adversarial machine learning attacks. To first begin with, we have the evasion attacks. So the evasion attack occurs in a situation where the data or input of a machine learning model is manipulated or tricked so that the algorithm can misclassify them. So by this case, we attacker deliberately makes changes within the images or the audio or any data, be it numerical data or anything that is going to be fed within this learning model during a training process, and then it will be altered, and then the model will misclassify them. So in one way, we said we can do it doing using perturbation. Perturbation, they make modification, and then add the adversarial noise. That one could be something that is slightly changed within the images, maybe contrast or resolution, and then the model will misclassify it as something else. So we can also have data poisoning. Data poisoning is a situation where attacker modifies the machine learning process by placing poison data within the dataset. This makes the output to be inaccurate or model misclassify the images, audios, and data. So data poisoning can be in a way that if the data set of dogs, I heard someone includes a lion. So in case someone includes a lion in the data set of dogs, then the machine learning model will be identifying a lion as a dog, which is one way adversarial machining attack can be executed. If it were told it was a data set of fake and real money, someone would include fake money within real money, and then that fake money, if it comes up, if the machine learning model comes across it to identify it as real money, yet it's fake money, that's giving out bad results. Then meaning the model is inaccurate or not competent. And then you can have model extraction or stealing. So in extraction, the attack occurs in a way that an attacker prods a target model for enough information or data to create an effective reconstruction of that model, or still data that was used to train the model. So in this case, the attacker will either steal the code and then modify it of the model, or the attacker would actually reconstruct the model and then give it different functions. So in this case, if at all, like maybe I designed a drone that is supposed to deliver goods, and this drone is supposed to go to certain uh, grid points, say maybe locations using the GPS. So when it reaches it, this point is supposed to drop the goods there and then continue. So if at all that someone reconstructs the code and then gives it something else, further to be delivering goods to different people that are not supposed to be receiving those goods. And then in another situation, an attacker can modify, for example, code of an ATM machine. And this ATM machine will be recognizing 2,000 note as a 5,000 note, or 10,000 notes as 50,000 note, which is a malfunction within the system. So in the picture here, I have a simple description of how these attacks are happening. As you can see, poisoning, the attacker is feeding poison data into the draining data set. And then the extraction, the attack is actually stealing data of the machine learning model and then is reconstructing it or modifying it. There you see the arrows coming from the machine learning model to the attacker. Then the evasion attack, yeah, the attacker feeds in wrong input into the machine learning model, and you see the arrows coming from the attacker to the machine learning model. Then we have white box and black box attacks. So these white box and black box attacks occur in a situation that a white box attack, this is an attack where attackers access the model's parameters and architecture, and then they can be able to modify them and then twist them around to alter the outputs. So in this case, the attacker attacks the model knowing its parameters or the way it functions. Then the black box attack, this one occurs in a situation that the attacker doesn't have the inner workings of the what? Of the model. So in this situation, the attacker will go to the model blindfolded, not knowing how its code works, and then he only knows the output, and then he may not also know the way it was trained, so you would depend on the outputs to determine what kind of attack to do. For example, what to change in the input, or what to change within the process of making the attack. Then we can also have targeted and untargeted attacks. So these are sub examples of the white box and black box. The targeted attack, in this type of attack, attackers disrupt the input in such a way that the model predicts a specific target class. So in this case, the attackers already know what output they want. So in that situation, the attacker will be able to modify the code in line to what he or she wants to get. For example, if the attacker wanted the ATM machine to increase his bank account balance, he would modify the code of the ATM machine to recognize a 20k note to 50k note, or a 2000k note to a 5000 note. And then untargeted attack. In this type of attack, the attackers disrupt the inputs in such a way that the model predicts a class, but it should not be the true class. So in this case, the attackers really don't know what output they will get, but they make sure the model misclassifies the data that has been input. So in this situation, for example, someone may change the sign, the red sign, or to something else, and then the model will be able to misclassify it to anything else. But all like there were traffic lights, it would maybe say green would be for go, but then in this situation it would be making the automated car to stop, which is still a malfunction within the system. Thank you. That's all. My colleague will take on from there.
Hi there, my name is Catherine, and I'm going to take you through the methods attackers use to target a model. So we are going to look at minimizing perturbations. So attackers use the fewest perturbations possible when corrupting the input data to make their attacks nearly imperceptible to security personnel and to the machine learning models themselves. So they take this approach to include limited memory. You could look at the Braden, Fletcher, Goldberg, Shannon algorithm. Okay. It is where it is used to craft adversarial examples, and they put in slightly perturbed inputs to fool a machine during the learning process. So what do they exactly do during the BFGS? You could say that they first define the goal, a small perturbation that when added to the original input, say our machine learning model is looking at a signpost, what could we put into that data so that it could misclassify it? Once they realize what this is, they decide to apply the BFGS, and this BFGS minimizes the objective function that is going to cause this perturbation. So after this perturbation is created, it will now make our model to misclassify what we have. In another one, you're going to hear of something called the deep fool. So usually the deep fool is used to search for an adversary with the smallest possible perturbation. But you could say that deep fool itself focuses on finding the closest decision boundary to a given input, and then it iteratively pushes the input towards the boundary until it crosses it. Then this is how it causes the model to misclassify it. Still, if you look at the example of a signpost, you could say that if we are looking at a red signpost that has the word stop, this model, if you have an adversarial attack using deep fool, it's going to cause this model to start not to identify the stop sign. It's going to look like another sign let us say maybe a yield sign, which is also maybe of the color red. Yes. So that is the deep pool. And we also have the first gradient sign method. That would be another one, and the Carlini-Wedger attacks. Now we want to look at something else. Another method that these attackers use is model querying. So here, the attacker queries or probes the model to discover its vulnerabilities and shortcomings. Then after that, it crafts an attack and exploits those very weaknesses. So we have an example called the zeroth order, and it is an optimization method. Yeah. Yes, so now I'm going to take you through the continuation, and we are looking at generative adversarial networks. So generative adversarial network have two components. We have the generator and the discriminator. So the generator creates fake data, fake but realistic examples. So that is the data we are talking about. While the discriminator itself tries to figure out which one of the data that this generator is bringing, is it fake or not. So if we have this generator creating more and more fake data, the discriminator itself will be good at classifying fake data only, and that would tend to be a problem. So let's first look at this picture here, and now we are looking at, this is a money making machine. Okay, so we get real examples, and the real money is taken through this discriminator, and the generator itself, they add in fake noise, and then it gets a copy of this real image and also prints out a copy of its own fake data. It's fun. Oh, yes, something like that. So when this discriminator keeps on receiving the data, it's going to judge which one is real and which one is fake. And for cases where things go wrong, this discriminator might end up falling more onto the fake side, causing the machine learning model to misjudge or misclassify the data it has been given. So we want to see the defenses against adversarial machine learning. First of all, we have the adversarial training, which is a process where the examples of adversarial instances are introduced to the model and labeled as threatening. So this process helps to prevent the adversarial attacks from occurring, but it requires ongoing maintenance efforts from data scientists, from data science experts and developers tasked with overseeing it. As I had talked about it before, you remember that if this discriminator from the guns, if you don't monitor it very well, it's going to get very good at classifying the fake data and will end up outputting more of the fake data, and yet we want it to see more of the good data. Yes, so we are going to look at more of this, and we are looking at defensive distillation. And defensive distillation itself makes a machine learning model more flexible by having one model predict the outputs of the other model that was trained earlier. When being trained with this approach, the algorithm can identify known traits. So this picture over here is what we look at, and this is a defense distillation model. So we have two steps for it. You have to train the teacher. You train the teacher with a neural network on the original data set using standard training procedures. Then after training the teacher's class probabilities, which contain more information than the hard labels, are used as soft targets for the next step. And the next step would be training the student. So the student itself, they can have the same or different architecture as the teacher network when being trained, but it will be trained on the soft targets from the teacher network itself. So the student network learns to generalize better by mimicking the teacher's output distribution, and this will bring more confidence levels for each class. So Knowledge defensive distillation is actually similar to GANs since it uses two neural networks, and as you have seen, we had the teacher and the student. We are going to look at examples of adversarial machine learning, and starting with, we are going to look at images, and an image is fed to a machine learning model as input, but attackers tamper with the input data connected to the image, introducing noise, and as a result, an image of a lion will get misclassified as that of an elephant. So in this example, you can see that we have a clean image and the machine learning model obviously classified it as a lion. But after adding a small perturbation to this image, this adversarial image over here, once fed into the machine learning model, it will be seen as an elephant, which as you can see is not the case. So this type of image classification attack is known as an evasion attack because it, instead of directly tampering with the training data or using another blunted approach, it relies on subtle modifications on the inputs itself that are designed to evade detection. Now, we are going to look at emails. Spam and malware emails can appear genuine, masking malicious intent. Now, the spam or the malware tricks the machine learning algorithm itself into incorrectly misclassifying as safe or not spam. So we can also look at signs. So when you look at signs, a self-driving car usually uses sensors and machine learning algorithms to detect and classify the objects. However, when a minor change is made to a stop sign, or one of those other things it's trying to detect an object, it can cause the vehicle's classifier to misinterpret this sign and potentially cause an accident. As you can see in this picture, we have this input image, and once it was put in this machine learning model, the algorithm itself, it was classified as a stop sign. But when we get this stop and then we add adversarial noise that you're seeing here, this adversarial image itself, once it's classified again by the machine learning model, instead of being seen as a stop sign, it is now seen as a yield sign. And this could cause fatal accidents.
I'm back again to explain the code that is going to be doing the adversarial machine learning. So first we have the inputs, the OS, we're interacting with the operating system, and then we have the touch that the core Python touch library for neural networks, and then we also have the optimizer for determining the neural network layers, and then we have the optimization algorithm here, and then we have one for loading standard data sets, the touch vision input data set, and then we have transforming the transformation, which transforms the model and data, and then we have the touch.utils.data.import, which loads and splits the data, then numpy for numerical data, and then we have the pill import image, which you can call the pillow. This is for image loading and manipulation. Then we have the matplotlib for the plotting graphs. So down here, we start by defining the data directory with the path to our data that we are going to use. As you can see, it's in my desktop folder CS2 machine learning stroke images.zip. Yeah. Then we have transformation where we transform the images. Then we have transforms to resize. This helps us to resize the images to be applied here to resize the image size. Then we can also have the below the data set. Data set is loaded from the image folder where we expect our images to be stored. Then we can continue down here to the training part and the splitting of the data set. So the train size splits the data into 80% train size, and then the test size splits the data into 20% randomly. As you can see here, we have the training int 0.8, the training data set having the testing data set having the remainder of the other part. Then we also train data set and test data set, split the data into two random sizes. Then the train loader and then the test loader, they both load the data set from our folder, and then the training batch size indicates that the training during the processing, 30 images are processed per training cycle, and then shuffle shows that via training, images are shuffled to improve generalization. Then the test dataset, we have the training loader, which loads the training dataset, and then the batch size is 1, meaning that one image is tested per testing cycle. And then we also shuffle through the images. Then we have the CCN model, what we can call a convolutional neural network architecture, which helps us into which helps us to design for binary classification. So this has the max loop, max polling, and then we can also have so basically this function here helps us to classify the images. Then we initialize down here. We're initializing the model. Initializing the model, declaring the loss function and the optimizer. So the first, which is the device, touch the device. This identifies where we are going to use a CPU or a GPU, and then this model initializes the entire CNN, and then also goes on to choose the device to use. Then the criterion, this defines the loss function, which is suitable for the multi-class classification. Then the optimizer optimizes the algorithm and sets the learning rate to 0.001. And then we move on to training the model. So training the model, we start with the average, which is equals to 10. And then we have the inner loop, the first loop that iterates through the data set. And then we also set the model to training mode. Then during that process, you also have the inner loop. So the inner loop iterates through the processed images, labels, and so on. And then we perform a forward pass using the outputs because models images. Then we also calculate the loss, and then we compute the algorithm. Here we compute the gradient, and then update the model's weight using the optimizer.step. Then lastly, I'll print out our output indicating the loss and also the training process.
Yes, I'm going to take over from my counterpart, Matthias. And we are going to be looking at the FGSM attack, which is the first gradient sign method attack function. So what is it? I didn't talk about it before, so I am going to give you a brief overview of how it works before we dive through the code. And it is used for attacking deep learning models, particularly the neural networks. So it generates adversarial examples by adding small, carefully crafted perturbations to the input image, and that's the image we have here. And then it maximizes the model's prediction error. So this perturbation is computed using the gradient of the loss function with respect to the input itself. So now we are going to come here, and as you can see, we are going to generate the adversarial example using the GFSM. So what do? We create sign data gradient, and then we shall call on the function, and we shall bring a perturbed image, and this perturbed image will be the image plus the epsilon times the sign data gradient. So then we shall also have the perturbed image getting the torch clamp, and okay, this converts, it will add the function itself to the image that is already existing for confusing the model itself. We are going to look at the model. We are going to evaluate this model after creating this attack function. And in this case, we are going to call on epsilon, and we are going to create this correct. So this correct is going to be counting the number of images that we find that are correct. And then the adversarial examples will be kept in the list. So as you can see, model.val will be setting the model to evaluation mode, ensuring that the dropout bunch normalizes layers and it behaves correctly. So what do? We are looping. As you can see, there is this for function. So it loads the images and labels them from the test folder, the test loader. Then it moves the data to the GPU if it's there, then enables gradient tracking of the images, as you can see here. Then it gets the output, it runs the model on original or on the green images, and then the torch max output 1 will extract the class with the highest probability. Now, if the model already misclassifies the image, it will skip to the next one. It will skip to the next one. Then we look at this block of code here, this one here, and as you can see, there is something where they say loss is equals to the criterion output, then comma labels. So it calculates the loss of the predefined criterion, likely the cross entropy loss. Then it calls on the loss backward function, as you can see here, to compute the gradients. Then it extracts the what? The gradient of the loss with respect to the input, which would be the data gradient. So now we are going to generate the adversarial example using the GFSM, and this would be it here. And it calls the GFSM attack, and yeah, it calls the attack function, and it generates the adversarial image. Now epsilon controls the attack strength that we are looking at. Now we are going to classify in the next block of code where we have this output. It classifies the adversarial image. So it passes the image through the model that we had, and then it extracts the predicted class. From here, it checks if the attack was successful here. If the model still classifies the adversarial image correctly, then it will increase on the correct ones. Otherwise, the adversarial example will be saved in the list that we had above, okay? So now, finally, we are going to compute the accuracy, and that is what we have here, the final this. the final accuracy. So we shall get the correct out of the length. This would be the number of images in the test loader that were loaded. And yes, it will compute the accuracy and give us the answer. So now what do? We say to rerun the attack using different epsilon figures. Now as you see, we called epsilon above, and this would be the figures that we have, the numbers, the values of epsilon. So this for loop function will loop through the values where epsilon would be 1, 0.01, 0.05, and as you can see, that would be it from us. Thank you.